Hello, my name is David Cox, and this is my Physics 2212 Lab 4 report. The purpose of the lab was to compare the mathematical and experimental results of resistor and resistor capacitor circuits with respect to their current, potential, and other physical properties of those circuits. Some of the physical concepts used in this lab were Kirchhoff's loop and node rule, which result from conservation of energy and charge, respectively, as well as Ohm's law, which you can see written there. Some assumptions and sources of error. Firstly, the wire and battery were both assumed to be ideal, meaning they had no resistance in those components, as well as the battery having no change in its charge stored over time. So obviously those two things don't occur in nature. So those were sources of error, but very small amounts of error. Additionally, the current of the circuit was kind of measured by proxy using the brightness of a connected light bulb with a known impedance, which is a source of error simply because it resulted in kind of an eyeball definition of when a circuit was, or a capacitor, I should say, was charged or discharged, which we'll get into later in this presentation. Some of the methodology. First, we used throughout the entire lab, actually, the University of Colorado Circuit Construction Kit, which is a virtual platform for experimenting with various electric circuit configurations and their physical results that will come from those. We first created just a simple resistor circuit, so just two 1.5 volt batteries, EMF of 3 volts total, wired in series, as well as two resistors wired in series with resistances shown there in the chart. The current was measured and calculated, and those values are shown. They are very, very similar, leading to some good amount of confidence in the software. Additionally, the voltage drop was measured across every component of the circuit, and those values are shown numerically as well as graphically on this slide. Importantly, you can see there that the sum of the potential differences across the whole loop is 0, which is consistent with Kirchhoff's loop rule, which we discussed just now. Next, after we created that resistor circuit, an RC circuit, or resistor capacitor circuit, was simulated. The resistor was a light bulb, and the capacitor had a capacitance of 0.2 farads, which did not change throughout the lab. Next, we used a digital stopwatch to measure the time to discharge and charge that capacitor, first with a 10 ohm light bulb, and then with a 20 ohm light bulb. After that, we swapped the light bulb out for a 30 ohm impedance light bulb, and we used that to measure the voltage drop across the capacitor over time. And we did that for 25 seconds, and we recorded that using screen capture. We then plotted those values in Excel, or rather I should say we plotted the natural log of those values with respect to time in Excel, and then we used a linearized curve of best fit, and we're able to determine a value for RC, which was the goal of this lab, using the following formula. Natural log of the potential difference over the initial potential difference is equal to negative T over RC, simply what that is. The results are shown here. The experimental value for the RC was 0.2, which is reasonably close to the calculated value of 0.166 repeating, which is simply quite literally 1 over simply the resistance times the capacitance, so 30 ohms times 0.2 farads is that. This is the graph of the experimental data and the expected data. You can see I've shifted it by actually 9 volts of the voltage, simply for visualization's sake. I felt that two lines on top of each other would be kind of hard to see, so I just shifted them there, kind of their intercepts. But you can see their parallelity, or I should say near parallelity, is really the thing we're looking for here. The fact that those lines appear to be very similar as far as their slope is kind of what we're looking for as far as our accuracy. So you can see here we have a slope of the blue line of negative 0.2 I should say, and a slope of the red line of negative 1.6, which is fantastic. What if we, instead of a digital ammeter in the experiment, we used a real one? Well, then when we flipped it, rather than like the digital one showing the same current, it would show the negative current, because those are programmed to measure conventional current, and flipping it would just be the opposite. Now, if no resistor was used, and we use this in a real physical circuit, because RC is effectively how long it takes to get to 1e of its original value, and that's a quote from the lab manual. If that makes 0, then it's near instantaneous. Now we know that wires have real resistance and that you can never get resistance down to zero, so that won't ever happen, but you could expect the amount of time it takes to charge a capacitor to be nearly, practically, I would say, instantaneous, not measurably different from zero.